Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a great pleasure to have John Blitzer here today. He's finishing up his PhD at UPenn with Fernando Pereira. And he's going to be talking about domain adaptation. If any of you are not on the schedule and would like to meet with John, there's a few spare slots, so just let me know and we'll fit you in today or tomorrow. Thank you.
Okay, so before I start, I want to give credit where credit's due, and that's to my co-authors. So Shai Ben David is a professor at Waterloo. Kobe Kramer is a postdoc with us at UPenn. Mark Dredzy is a fellow grad student. Ryan as well, he's now at Google, and Fernando Pereira, my advisor. Okay, so what I am going to address today, the problem I'm going to address, is hopefully something everyone who's used statistical models ever has encountered. And that's this problem that you train up a model on a training set that you built yourself, and you test it as best you can, and then you go to apply it in the real world, and it works much worse. So this often happens in vision, where let's say you're doing face recognition and you take pictures of people's faces under good conditions, but then when you actually want to recognize them, there's occlusion or differences in lighting. Actually now there are people in our group working on gene finding, and you may have good curated and annotated gene sequence data from one organism, but actually you want to apply the model in a different organism, and it might not work as well there either. So probably the classic example of this for people who work in applications of machine learning is in speech, where you may have transcriptions for one person, but you want to use your speech recognizer for a person with a different accent or vocal tract length. So in text, which is what I'm going to talk about today, this problem is particularly acute because there's a huge variation in the vocabulary that people use across different domains and styles. So if you think about it, there's financial news and blogs and scientific text. And one option you could obviously say there is, suppose we want to build statistical models, why don't we just build one for each domain? Well, okay, this works well initially until you think about, well, okay, so if we're building a statistical model for language, typically you need annotated data from a human being to help you at train time, and so you need to annotate each separate domain. And then again, each domain, of course, there aren't really three domains, right? Each domain has many different subdomains, so a blog, there isn't just one domain of blogs. There's political blogs, tech blogs, and so on. And even within each domain, there are even more. So in essence, it's hard to tell what exactly you would want to annotate even there. Okay? So I want to start off by talking about an example, a specific example for the problem that I'm going to address in this talk. So this is sentiment classification for product reviews. So here, what we want to do is get a review of a product, so a piece of text that basically says whether or not what someone thought about a product he or she bought. And we're going to pipe it through some classifier, an SVM or naive Bayes or what have you, and get out that the person either thought had a positive sentiment about a product, thought the product was good, or negative. The person didn't like the product at all. Okay? So where's just actually to stop here, there are actually startup companies that are now doing this. I've seen people that are interested in you type in a product name and you get back a bunch of search results of various blogs, and they say, they group them for you by whether or not the blog was positive or negative about this product. So you type in iPhone, it tells you, this person liked it, this person didn't like it, and here's what they said. Okay, so where's the adaptation problem here? So you can think, so I'm envisioning a scenario where you have reviews of one type of product, and for each review you have a label. Someone went through and said, this review expresses positive, this one negative, this one positive, and so on. But what you want is you want to take a model learned on this type of product and apply it to a very different type. Okay, so let's say you have book reviews and you want to actually know whether reviews of kitchen appliances are positive or negative. Okay, so let me actually let me read to you guys two examples of reviews just to get you a feel for the type of data we'll be looking at. So this one is a book review we pulled off Amazon, and I'll read it to you. Running with Scissors, a memoir. This book was horrible. I read half of it, suffering from a headache the entire time, and I eventually lit it on fire. One less copy in the world. Don't waste your money. I wish I had the time spent reading this book back so I could use it for better purposes. This book wasted my life. And another review, also from Amazon, of a kitchen appliance. I love the way the Tefal deep fryer cooks. However, I'm returning my second one due to a defective lid closure. The lid may close initially, but after a few uses it no longer stays closed. I won't be purchasing this one again. Okay, so just to illustrate, what I've labeled in blue are ways of expressing sentiment in books that may not really be applicable to kitchen appliances. Right? These are the differences in vocabulary that I'm talking about. Right? You read half of a book, you don't read half of a Tefal deep fryer. Again, for kitchen appliances, you get things like words like defective. Right? You would never say, this book is defective, I'm returning it, it just doesn't work. Right? These are ways of expressing negative sentiment about kitchen appliances that you don't use to talk about books. Okay. So, and just to give you guys an idea, so if you train a classifier on books and to actually do this problem and test it out on kitchen appliances, the error doubles. Okay, so this is a real problem. This vocabulary is actually causing us to get a lot of things wrong in this new domain.
And what's the error when you train on kitchen appliances?
When you train on kitchen appliances, it's actually even lower. It's, I think it's 11 or 12%. We'll see the results actually at the end. Okay, so before I talk about the specific model that's the focus of this job talk, I want to sort of introduce a setting here for us, which is linear models. So these are the kinds of models we'll be addressing today. So the idea here, probably everyone in this room knows this, but to get us on the same page, what we're going to do for a particular instance is we're going to represent it as a vector in a high-dimensional vector space. Okay? Each dimension in this vector space is going to represent a single word, or in this case, a bigram. And what this, for a particular document, the positive entries, the non-zero entries in this vector, will be those words which occurred in the document. And typically, what people do and what we'll do here for sentiment classification is that each entry in the vector kind of indicates how much of the document has been devoted to this particular word or bigram. So this is also often called the bag of words representation. And in our case, there's also some bigrams, so bag of words and bigrams here. At the same time, we have a weight vector, and each entry in the weight vector kind of indicates the propensity of a particular word to indicate positive or negative sentiment in this case. Right? So horrible has a -1. That means that it's going to basically express negative, a word which contains horrible, that a document which contains horrible, that gives you some indication that this document is expressing negative sentiment. The way we're going to actually do classification is simply take the dot product of the weight vector and the feature vector, and if that dot product is negative, we'll say this expresses negative sentiment. If it's positive, it expresses positive sentiment. Okay. So in this talk, we're only going to address this binary classification problem, but I want to mention that basically the methods here apply, this kind of feature vector representation in linear models apply for much more complicated problems. They've been used for sort of structured segmentation and labeling problems and even machine translation. So the basic techniques are going to apply throughout. What I also want to mention, though, is where the domain adaptation problem kind of crops up in these models, right? So if we're training only on books, we've never observed the feature defective, right? So we don't know what to do with it. The best we can possibly do here is just give it a 0 weight, right? We haven't seen it before, so it's only natural that we give it a 0 weight. And then when we come to it at test time, we don't know what to do with it, right? We don't know how to actually use it in classification. Okay, so structural correspondence learning is a method that's the focus of this talk, and that's going to cut adaptation error by more than 40%. And the basic idea here is just to use unlabeled data from the target domain. And we're going to use that to induce correspondences between features in the two domains. So what I mean by this is words like headache for books are kind of correspond to words like defective in kitchen appliances, right? So both of these express negative sentiment, so if we could somehow figure out how to align them, then we could train a good classifier for the kitchen appliances domain using labeled data from the books domain, right? So we would if we had a good correspondences, we would automatically get a good kitchen appliances classifier using books data. So for those of you who are more familiar with speech, actually, as far as I know, we are the first ones to use unlabeled data to do adaptation for text. But this is a really common setup for speech, the speaker adaptation problem, where people do what's called maximum likelihood linear regression. And the technique itself is quite different, but just to familiarize you guys, the setup is basically the same. Okay. So SCL works in 2 steps. The first step, we're learning a correspondence mapping, and that takes instances from the source domain and from the target domain and maps them onto a shared feature space, and we're going to call that phi. So we learn phi from unlabeled data, and then for labeled data, we just take the feature representation that we learned from the unlabeled data and use it as features for a linear model, right? So we have phi. Now we can learn weight, a weight vector v, which simply multiplies phi instead of multiplying the original feature vector x. So if this new feature vector represents good correspondences, then we can train a good model this way. Okay. Just to reinforce what the desirables for phi should be, right? So firstly, we know that phi needs to make the two domains look as similar as possible. But if we're projecting into a low-dimensional space, we want to make sure also that we don't lose our discriminative power, right? Our original feature representation, we designed it because we thought we could do classification well in this representation. So we couldn't, for instance, take all instances and map them onto a single point. We also want phi to allow us to do good classification. Okay, so let me give a quick example about how this is going to happen. So going back to our review of a kitchen appliance, we have something like the word defective. So, and we know we need to figure out whether this expresses positive or negative sentiment, right? One thing we can do is look up in all the kitchen appliances data, look up the unlabeled context for defective. So these are things like, do not buy the Shark portable steamer, the trigger mechanism is defective. The very nice lady assured me that I must have a defective set. What a disappointment. Maybe mine was defective, the directions were unclear, right? So what you can see is that what I've highlighted in blue here are words which potentially apply equally to both books and kitchen appliances, right? You can be disappointed with a book and you can be disappointed with a kitchen appliance, right? So let's quickly take these words and look them up in book contexts. So this book is so repetitive that I found myself yelling, I will definitely not buy another. A disappointment, Ender was talked about for some number of pages. I think it was 12 pages altogether. This guy really liked a character named Ender, and he wasn't featured enough in the book. It's unclear, it's repetitive and boring. Okay? So again, words like boring and repetitive and bigrams like number of pages, now we can say, defective, actually, we can tentatively align the word defective with all these features from books. And since we have labeled data from books, once we do this alignment, we can automatically deduce something about defective, right? This is the intuition for SCL. Okay, so the key notion in SCL, and what I've highlighted in blue here, are what we call pivot features. So pivot features are features that occur frequently in both domains, and they characterize the task we want to do. And typically, so I showed you 3. Typically, we choose hundreds or thousands of pivot features to help us align these two. And we need to choose them using the data we have, right? We don't have labeled target data, but we have some labeled source data, and we have unlabeled source and target data. So let me give you guys just 2 ways of choosing pivot features. One way is to just take words and bigrams that occur frequently in both domains. We call that SCL. Another way, which we're going to call SCL-MI, is just like this, but you also choose it based on mutual information with the source domain labels, right? So if you think about books and kitchen appliances, you have labeled instances from books, so you can take features that have high mutual information with the book labels. Okay? Then give you guys some examples of this. Here are some SCL potential pivots. So these are words like about, when, like. They may not be great pivots for helping us do discrimination, right? On the other hand, if you use the mutual information, you get words back that, bigrams and words back that look like they would be very useful, right? Things like don't waste, awful, highly recommended, loved it. These things look like if we could somehow align features from the 2 domains with these words, then we would be able to do good classification. Okay, so how are we going to actually use these pivot predictors to align things? The basic idea, I want to go back first to this example that I showed you guys before, using not by as a pivot, right?
In the previous slide, are both those things pivots or just the MI ones?
So these are 2 alternative methods for selecting pivots, right? And I'll show you actually how, one thing is at the time for results, I'll show you how the method for selection can make a difference in the final results of the classification. Yeah?
But you never used in any way the fact, you're saying that you want to use words that characterize the sentiments.
Right.
And I was thinking that you're going to get the words with very high weights, either negative or positive. In that case, you didn't use that.
That's right. So mutual information is kind of a proxy for that. But you could think of it exactly as you're saying, another method that, chose the words with the highest weight, or did L1 regularization and chose the features that actually were on in the final classifier. Mutual information is just one proxy, but we can talk about that later. Okay, so you have this pivot not by. How are we going to actually align these other words with this pivot, using this pivot, sorry. So the idea here is just you mask the pivot, cover it up in each instance, and try to predict its presence or absence using all the other features in the instance, right? So we have a binary classification problem. Does the phrase not by occur in this instance? Okay? Now remember I said we had hundreds or thousands of pivots. Say I'm going to call this hundreds or thousands n. So if we can train n linear predictors, one for each of these binary problems, right? And each of these linear predictors is going to be characterized by a weight vector. So the thing to note here is that each pivot predictor is going to implicitly align non-pivot features, right? How? Because if you think about the weight vector for not by, right, the one prediction problem not by, if repetitive and defective both have positive entries in this weight vector, then we can kind of tentatively say, aha, maybe these 2 things should be aligned. Okay?
This is still a bag of words.
This is still bag of words, yep. Okay, so if we collect all our pivot predictors, there are n of them, and put them in a matrix where each column is one weight vector from a pivot predictor, note that if we multiply an instance vector x with this matrix, we get back what amount to basically a bunch of features. Each one kind of tells you the propensity of a particular pivot to occur, right? So if you think about the value of the ith feature sort of says, what do I think about the phrase not by occurring in this instance, right? So this gives me, let's say, 1,000 new features. But we don't really want 1,000. We want something fewer, something more compact. And the reason for this is that a lot of these pivots we selected are going to duplicate information, right? We expect them because a lot of words are synonyms, right? Horrible, terrible, and awful are roughly the same as pivots, right? So what we're going to do is compute the singular value decomposition and take the top left singular vectors here. Note that the top left singular vectors are the best orthogonal representation for the space spanned by these weight vectors. Okay? So for those of you that kind of have looked at unlabeled, unsupervised learning for text before, this is not an unheard of approach. But I do want to highlight a few differences between SCL and these two approaches. So the first is that by choosing the pivots, actually, so these two methods both do dimensionality reduction on the document by feature matrix, right? By choosing the pivots judiciously, we can actually make a big difference in the resulting representation. And the second is that we're actually learning these weight vectors discriminatively in this binary prediction problem, right? So in practice, co-occurrence data, there may be big dependencies among different features, right? Terrible and awful may both be very good predictors of horrible, and so on, right? The ability to train these weight vectors discriminatively also can make a difference. Okay. Mm-hmm.
Is 1,000 too many just for speed reasons?
1,000 is too many, both for speed reasons and for statistical reasons. But actually, I think we should talk about that offline. Okay, so now on to the second step, which was just supervised learning. So if you remember now, we have our instance vectors x, and we also have the low-dimensional feature vectors, which we get by taking our top singular vectors. So say we take the top 50 and multiplying x with them. Right? And if we take the top 50 singular vectors, this is going to give us back 50 real-valued features. Right? Now, how are we going to use these? Well, we just train another linear classifier, and we have both the original features x, which are weighted by w, and the new features phi times x, which are weighted by v. Okay? At train time, we're just going to learn w and v together to minimize whatever your favorite loss is. And at test time, we first apply phi, and then we just apply w and v. And that's how we do test classification, right? So this is source data, i.e. books in our example, and this is target data, like kitchen appliances. Okay? All right. So before I go into so that's SCL. That's the whole of the algorithm. Before I go into the empirical results, though, I want to just state a few papers which maybe you guys know, which kind of inspired me to do this work. The first is alternating structural optimization, which is a semi-supervised method. And the idea I took from here is this idea of learning predictors based on unlabeled data. And the other is, for those of you who work in dimensionality reduction, is this idea of correspondence dimensionality reduction. So you have a low-dimensional representation, like maybe a manifold or a linear subspace, and you have high-dimensional correspondences, and you want to learn two different data sets with high-dimensional correspondences. You want to learn a low-dimensional representation that respects those. Okay. All right, so now on to the data. As I said, these reviews are from Amazon. So we just pulled down a bunch of product reviews from Amazon. And we have books, DVDs, kitchen appliances, and electronics. Okay, these are our 4 domains. And we have 2,000 labeled reviews from each domain. And we also take between 3,000 and 6,000 instances as unlabeled data. Now, we're treating this as a binary classification problem, which is actually pretty standard in the sentiment literature. We just say if something has 4 stars or more, we call it positive. If it has 2 stars or fewer, we call it negative. As features, we're using unigrams and bigrams. And As pivots, this kind of goes to your question, we're going to either use the SCL pivots, which ignore mutual information, or the SCLMI pivots, which include mutual information in the choice of the pivots. Okay. And at train time, we're just going to minimize a Huberized version of the hinge loss. And it's roughly, basically, it's a differentiable version of the primal optimization problem for an SVM. Okay. So, but before I show you guys the results, I want to briefly illustrate the kinds of projections you can expect to get out of SCL. So in the top left here, so I'm showing you one column of phi, right? One projection from the original feature space onto the real line. On the top left are features that only occur in the books domain, don't occur at all in kitchen appliances, and are negative under this projection. Right? So these are words like plot. Well, if you mention the plot, you don't like it. Number of pages, predictable. If a book is predictable, you're being negative about it. For kitchen appliances, these words don't occur in the books domain at all. The plastic, if the plastic handle breaks off, something's poorly designed, you don't like it. If books don't leak, kitchen appliances leak. For positive things about books, you get fascinating, engaging, must-read. Grisham, actually, people on Amazon really like John Grisham. And they use actually the word Grisham not only to describe his novels, but also, this book reads like a Grisham novel. That's a big compliment. So for kitchen appliances, there's espresso. Espresso is like the John Grisham of kitchen appliances. People just like espresso. Are perfect. Using this as a breeze. I've been using it for years now. And again, well, let me finish the slide. Okay, so the important thing is to realize here is that even though we've never observed any of these features in the books data at all, under this projection, we can learn something about them from the labeled books data because we have these books features. Right? This is how we expect SCL to help us. So
the question I had is, do you ever have you handle words that actually may invert their meaning? Like maybe the word simple.
Yes. Yes, you do have that. And actually, basically, there are very, very few of those, something like less than 1%. We looked at this. Something like less than 1% of the words do this. But this can actually happen for features in other areas, and in particular, I think in some areas that you guys may be interested in. So let's talk about this later on after the talk is done. So now on to the actual empirical results. Let me help you guys parse this because it's a little bit complicated. So first, in red here, I've labeled the domain that we're actually adapting to. And these thick red lines are roughly the kind of gold standard, the results you would get if I had, so in the case of books, 2,000 labeled books reviews to train on. What kind of accuracy numbers would I get? Same thing for DVDs. On the x-axis, each group here is an adaptation from one particular domain. So this is from DVDs, train on DVDs, test on books. Train on electronics, test on books, and so on. The black bars here are the baseline if you don't do any adaptation at all. Blue is SCL if you just use the SCL pivots I showed you before, and green is SCL-MI. So in particular, if you think about this guy, here the baseline loss due to adaptation is 7.6% from 80.4 to 72.8. And the SCL-MI loss is 0.7. So in this case, SCL-MI can do almost as well as if you had real books data to train on. Right? Here's the example for electronics and kitchen. And again, the thing to note here is that so kitchen and electronics are actually very, very similar. Kitchen appliances are really a kind of electronics. So the vocabulary people use is pretty similar. And here you can even get kind of a semi-supervised effect where actually SCL-MI can do better than the original electronics data by just training, by having so much unlabeled data. Okay? But the results that I want to focus on briefly here are these from kitchen to books, right? So something's gone wrong here. Actually, SCL-MI has increased the error of the classifier. So what's happened is that we've kind of misaligned features from the two domains. And the reason this happens in particular in this data set is that on Amazon, there are really a huge number of books. And they're all different kinds of books, right? There are, there's Christian literature, there's fiction, there's, history. But there really aren't that many kind of kitchen appliances, right? Basically, if people use different vocabulary for kitchen appliances, chances are they're just being either positive or negative. So what happens is projections that look discriminating for kitchen appliances actually are kind of topical projections for books. So you say, this is basically doing grouping things by sentiment in the kitchen domain, but unfortunately in the books domain, it's just discriminating based on topic, right? And so this can cause you to get larger errors.
Maybe it's like picking out the reference books or something.
Right, or just saying, people say, the words, Jesus, God, and the Holy Spirit in Christian literature, right? And but as opposed to history where they use some other vocabulary, right? So it basically actually is discovering different topics, but there aren't that many. What I'm saying is the books domain is much more diverse in the vocabulary that people use in the reviews, right? And so modeling the variance there actually, which is exactly what the SVD does, there's just projections that don't discriminate based on sentiment in the books data, but they do in kitchen appliances, right? And that's the mistake that's made. Okay, so if you wanted to, yes.
Did you do an experiment where you did SVD, not using the pivots or anything, but just do SVD sort of on the target domain and just learn? I don't know if there's seems like it's hard to tell how much of your gain comes from the dimensionality reduction and how much is coming from sort of the pivoting.
Right. So we don't have those experiments here, but we did do them, and actually SVD, on this task it helps a little. On many of the other problems, it doesn't help at all. So it basically you're kind of dependent on luck there. So I guess we should probably take this offline. But so in the experiments we've done on all these domains, doing SVD is consistently worse than this. Sometimes it can help a little bit. Sometimes it doesn't help at all.
Can you say something about why books to DVD also didn't seem to work?
Yeah. So books to DVD is so this is actually this difference here is fairly small. It's 1.4%, but it's the same. We've observed that it's the same sort of problem. There are projections in books that look discriminating that we've somehow misaligned to DVDs, right? It's not necessarily so it can happen more acutely when you have one domain that has much lower variance, but you can still get the misalignment if you have lots of different ways two domains can differ, right? So DVDs and books are the richest two domains in this data set that we have, in the sense that they're...
Books work really well.
Right, so DVDs to books actually work really well. And the reason for that is that when you learn the low-dimensional projections for DVDs, it aligns exactly to those discriminating projections for books, right? So I want to actually move on to show you guys how we're going to fix this problem.
I don't understand that as a reason, though. It sounds like it's more like an explanation. And it's like that's what happened, but it's not why it happened, right?
Right, so we know, we know that there's misalignment. This is what we observed. And this is, I'll show you here how we're going to fix it, right? So we can discuss whether there might be actually a better way to fix it as well, but I just want to press on here. So we decided that you need to basically know a little bit about the target domain in order to fix this problem. So what we said is if what could be the minimal amount of effort that someone could put in? So remember we had 2,000 labeled instances. What if someone just labeled 50 instances for us? Could we exploit that to kind of correct these misalignments? Okay. So, and the answer is we can. So the method we're using is we just, at source train time, we save the weight vector for the SCL related features, right, the projected features, and we're going to call that VS. Now, on the target data, we only have 50 instances. Let's just regularize, instead of centering, let's say, a Gaussian prior at 0, let's center it at the weight vector that we have. Okay? So here's the optimization problem if you look at this. So the first is just your favorite loss. Mine is the Huberized hinge loss. The second term is just telling us we only have 50 instances. It's unlikely that we can learn a lot from unigrams and bigrams from only 50 instances. But if we look at just the low-dimensional features, say we have only 50 projections, and we say, keep those close to the source weights because I hope that most of the alignments are good. Now, so keep these close to the source weights. I hope that most of these are good, and the resulting weight vector V will just correct the things that had gone wrong, okay, in the target domain. So this actually, this method here was inspired by two people at Microsoft, and the difference, though, that I want to highlight between this particular technique and the technique of Chalba-Nacero is that they propose using the high-dimensional features, right? We actually are explicitly avoiding using the high-dimensional features in this regularization scheme. So they say, keep the high-dimensional weight vector close to the high-dimensional weight vector from the source domain. Okay, and we're actually advocating using the low-dimensional weight vector here. Now, so if we go back to the results, I'm showing you fewer results, but these are just the results where SCLMI did the worst before. So the thing to note here, so the baseline is the technique of Chalba-Nacero here. And the SCLMI uses our own technique, which regularizes based on just the low-dimensional features. Right? So the thing to note is that in this case, SCLMI consistently is improving over our baseline, right, in every case.
So the baseline is stronger than just using the 50 to train?
It's using the 50 to train, so it uses exactly what Chalba-Nacero proposed, which is train a weight vector, train a model in the source domain that gives you a weight vector. Call this WS. This weight vector multiplies the unigram and bigram features. Now on the target domain, regularize WT to be close to WS in the same way that we regularize V to be close to VS.
So what happens if you just do the naive thing of taking the 50 label guys and just training classifiers with those?
That does much worse. That does, typically below 65 across the board. 50 instances is just not enough to learn anything useful on this problem. Okay, so I've shown you guys a lot of results, so let me kind of give you a bit of a summary slide here. So the first thing I want to note is that even without any labeled data in the target domain at all, SCLMI reduces error due to transfer by 36% from 9.1 to 5.8. Adding 50 target instances without regularizing based on the SCL features doesn't help you at all. Because these high-dimensional features are useful, but only when you have enough data to get a really good sense of what they're doing. On the other hand, using them by using the technique of Chalba-Nacero on the low-dimensional feature representation, you're actually able to get an even bigger win and reduce error by 46% from 9.1 to 4.9. Okay. Yep. Mm-hmm.
So what surprises me is that SCL gives you such a big improvement because it seems that you're selecting mostly stop words there.
Yes. So I was a little unfair to SCL in that slide of the example. What I showed you were features that were in SCL but not in SCLMI. Right? So I showed you the symmetric difference of the two. Actually, SCL does have a lot of good features in there, pivot features in there. Okay, so I'm going to actually switch gears for a second here and talk a little bit about some learning theory work for domain adaptation. So the setup here that we're going to address is where you have training and testing data that are drawn from different distributions. So this represents training data from a source and a different distribution for the target data. Okay? And the idea here is to exploit, again, we're going to want to exploit unlabeled data. Here we're going to do something slightly different. We want to be able to give a computable error bound for domain adaptation. Okay? And I'm going to show you at the end kind of using these bounds in what I'm going to call an adaptation active learning experiment. Okay, so first, a bound on the, probably the simplest possible bound you could state for the adaptation error. So let me read it to you briefly. Let H be a binary hypothesis if script E is the set of measurable subsets of X and ds and dt are source and target distributions with ps and pt as their density functions, then the bound we can state is that the target error is less than or equal to the source error plus the L1 difference between the two distributions, the absolute variation, total variation, or L1 difference. Another way to write the L1 in terms of the measurable subsets is that you just take the subset on which the probability mass differs the most. Okay? And so that's actually what we're going to focus on here. This actually has two disadvantages for us. Firstly, the difference across all measurable subsets can't be estimated from finite samples for arbitrary probability distributions. So we're going to want to state a distribution-free bound in the style of Vapnik and Chervonenkis. And we won't be able to do that if we use, we won't be able to state a computable distribution-free bound if we're using this metric. Right? The other thing is that we're really only interested, we're not interested in all measurable subsets, right? We're interested in differences in the distribution that cause us to make mistakes for the classification problem we're doing, right? So we're actually interested in a very specific problem, like for us, it was sentiment classification. We don't really care if, there's some wild, badly behaving subset on which the two distributions differ if it won't cause us to make a mistake, right? So the idea that we're going to use here is what I'm going to call the delta H distance. So the basic idea is that we want to measure subsets where hypotheses in H disagree. So here's the definition. Let H be a hypothesis class and denote by H delta H the set of subsets in X where two hypotheses disagree. Then we have this definition for distance, right? So if you look at the subsets A here, this is kind of like the error sets of one hypothesis with respect to another, right? So if you think about, I give you a specific hypothesis, I look at all the other hypotheses in my class and look at the error sets on which the two distributions differ the most, right? So this is like saying, well, if I had a particular classifier that I trained on the source data, where in the target data could I potentially make the most mistakes with respect to other hypotheses in my class? Right? So this is intuitively kind of what we care about for domain adaptation. So let me actually say the properties of this that are important. So first, notice that it's always lower than the L1. It's in particular, it's you're not measuring all of these subsets A are measurable, but you're not looking at all measurable subsets. So that's one thing that's convenient if we're stating an upper bound. It's good for it to be lower. The other thing is that what's important for us is that it's computable from finite unlabeled samples. And that just to say how we're going to actually compute it, there's actually a very simple procedure, right? If I give you two big unlabeled samples, I label the source data as -1 and the target as +1, and I just train a classifier to discriminate between the two. The error of that classifier is exactly this distance. In particular, you can directly compute this distance from the error. So if you think about it, when the error of the classifier is very small, it did very well discriminating between the two, so they have very high distance. On the other hand, when it's very large, you couldn't really distinguish between the two, so it's actually got a very low distance. Right? And yes, in addition to that, it is a real distance. And the paper where this measure of divergence between distributions was introduced as a paper by Shai, actually in the context of streaming algorithms. But we're going to use it for a pretty different context here. So I said you can compute an empirical quantity of this. When we have unlabeled samples US and UT, I'm just going to write d hat h delta h to indicate the empirical h delta h distance. Okay. The other tool that we need is what I'm going to call the optimal joint hypothesis. So this is the hypothesis that achieves minimal error on both the source and target domains, right? The sum of the errors on the two domains, right? So this is like saying, what's the best single hypothesis for both domains, okay? And lambda is actually that error, the error of this hypothesis h star. And, okay, well let me say one quick thing about this. Actually, h star is kind of embodies what I will call the domain adaptation assumption. If you think about SCL, we needed there to be actually one good classifier. You don't necessarily have to know it, but there needs to be one in order to avoid using the target data at all. A setting where this wouldn't be true is if, actually, to address your point, is when you have lots of features that may switch polarity, right? That's something where you wouldn't have one single good classifier. Right? So in order to have lambda be low, you need to have a single good classifier. And features that, in our case, sentiment classification, very few features would kind of switch polarity on you. Okay. So now let me briefly run you guys through this bound. So this is the final bound. Let H be a hypothesis class of BC dimension D, and US and UT be unlabeled samples of size m prime each, drawn from DS and DT. With probability at least 1 minus delta, we can bound the error of every hypothesis in H in terms of, first, its source error. Second, the H delta H distance between domains, which now we know we can compute from the unlabeled samples. And actually, let me address this one before going back to lambda. We can compute it from unlabeled samples, but of course, we need to have if the unlabeled samples are small, our estimate is not going to be as good. But luckily for us, there is uniform convergence of this estimate. And it converges at the usual rate. The thing to notice, though, is that if we actually have very large unlabeled samples, and these may not be hard to get, this term can get small pretty quickly, right? Okay, so now lambda kind of indicates that we can't possibly do better than this ideal hypothesis, right? But if the error of the ideal hypothesis is small, then I can tell you basically exactly how well you're going to do using only unlabeled data from the source and target domains, and a labeled source training set as well.
So we can't estimate lambda.
You can't estimate lambda. Well, you can, but actually we can show now that estimating lambda is basically as hard as doing classification. So in essence, you can't gain anything from trying to estimate lambda. This is so basically this is kind of the rub here in these bounds. You basically need to say, well, I've kind of intuitively in my head set up a problem on which lambda is small, right? Like the sentiment data where you say, well, maybe the two domains are very different, but these differences are ones that you can account for with unlabeled data. It's not like someone sort of pathologically gave you the same. So you could think of someone who trains a weight vector on the source domain and then flips the sign of every entry, right? You basically, there's nothing you can do there, right? So this is the kind of setup we're saying, think of a reasonable problem where you actually can train a good model on both domains, and now the differences can be accounted for using only unlabeled data. Mm-hmm.
So maybe I'm not understanding everything, jumping ahead. So you're saying that if lambda is small, you can actually take unlabeled data and estimate how big those bars are going to be that you showed earlier, that you can estimate?
Exactly, yeah, exactly.
How far off?
Mm-hmm.
But you might not find a classifier that does both that does well on both. But
that's right.
Find just one. Your target is to adapt it, right? Is not to have something that does work on both.
Yeah.
So that's a very loose bound in some sense, because that lambda says how good you can do on both.
Right. So no, you're absolutely right. The problem there is that, remember, we only have source labeled data, right? So you may actually be able to find a good target classifier, right? But you need target labels to be able to do that, right? If you only have source labels, you might actually get lucky and by some statistical anomaly actually find a very good target classifier on, let's say using only 2 source examples. But the problem is, in general, if you only have source labeled data, you can't hope to do better than the optimal joint hypothesis. Actually, I will advertise something in about 2 slides for you on this problem. So let me go on to this adaptation active learning experiment. So the kind of setup I'm envisioning is you have a bunch of different domains. You have unlabeled data from each one. And we want to ask the question, which domain should we label? Okay. Again, we're going to train a classifier to distinguish between these unlabeled source and target instances. And those domains, we want to pick the domains to label which kind of give us the most coverage, right? So we're going to use as a proxy h delta h distance the margin of this classifier on the unlabeled data. So if something has very big margin, then we're going to say these things are very different, right? And again, what I said is you want to label domains to cover the most. So if you think about our domains, intuitively, you'd like to say, well, I don't want to pick both electronics and kitchen because this is going to duplicate work. I'd like to pick one of each of these 2 kind of clusters of domains. Right, so here are the results. Again, the h delta h distance we get by training a classifier to discriminate between the 2 domains. And on the x-axis, I'm showing the proxy h delta h distance. On the y-axis, I'm showing you the actual adaptation loss. So you can see the relationship is pretty much linear. This is the line of best fit here. And again, to kind of relate the problem of picking domains to label, if we chose both electronics and kitchen to label, then that kind of puts us in this red region, because for DVDs and books, we're going to be, on average, it puts us basically here, right? For books and DVDs, we're going to do roughly about as poorly as this point or this point. And again, if we split them, say choosing, let's say, kitchen and books, we would be somewhere in this blue region here for adaptation loss, so much lower down, right? So actually, so the point here is that h delta h distance is a pretty good proxy for actual error in this problem. In particular, this is because of the assumption that lambda is low. Okay. So I want to end on a kind of speculatory note for this group, which is the relationship between some of the techniques I talked about here and ranking, right? So I'm kind of envisioning a scenario where you get a query as input, you get a query and a list of top-ranked documents from some initial retrieval engine. And what you want to do is re-rank these documents so that the most relevant ones are on top. Okay? And you might have some editorial data, you might have some click-through data, but you have some sort of method for getting feedback for this, right? And the adaptation problem I envision is something like different markets or different query types. So let's say I have a lot of really good editorial data for American English, but in Indonesia I don't have anything, right? Or I have very little. What I want to be able to do is align different features, and these could be actually, so I've talked to you about linear models. Maybe we should talk a little later in one-on-one meetings about kind of ways to use this for the more nonlinear features that I gather you guys are making use of here. But you can envision that between the US and Indonesia, there probably are some common relevant features, and you want to just align the ones that you haven't observed before with labeled data in, say in Indonesia. Let me say just briefly what I meant by query type is I actually can envision a scenario even in US English where you've got some editorial data for Britney Spears, but not much for Gaussian processes. I'm sorry, guys. It's just it's a sad fact of life. But you want to be able to have a good ranker for queries about Gaussian processes. Okay.
My question was, I think you could argue that in lots of domains, there's many sub-categories. Imagine you just had the Amazon data and you just had a giant blob of reviews.
Yeah.
And they weren't categorized into groups. The question I have then is, how would you go about deciding
what the groups are?
What things to be labeled? Would you have to cluster them first to say these are the groups, or could you somehow do this just based on, I don't know, some other mechanism? Because I guess exactly what you have in queries is that there are these nebulous groups of queries. There's navigational queries, for example, and there's exploratory queries. There's queries people looking for lyrics, and trying to make airline reservations, whatever. We don't know what they, which ones we do well at.
So I can answer that in kind of two. Okay, so this is the end of the talk, but let me give you guys first the advertisement slide, which is so for people that are interested in learning when you do have some target data and you think you can learn a good classifier there. We actually have a paper in submission on learning bounds for that case. And for those of you who are kind of more NLP people, I can talk about applying this to kind of, I guess, problems with more complex output. Problems like segmentation or tagging or parsing. And we have results there as well, but they didn't make it into the talk. Okay, so thank you. And let me address that question. So you can learn from only unlabeled data. You just basically take as pivots just frequent words, right? The problem that you encounter is that the more unlabeled data you kind of throw in, the more different kinds of domains, the less sure you can be. So one setup I can imagine trying is something analogous to backoff, where you have a single representation, then you cluster and have representations for the clusters, and so on down the.
I was assuming you had no unlabeled data. No labeled data. You have a chunk of labeled data. You just don't know which ones you want to label. And I guess the question of which ones you label next is sort of related to the class of them.
I see.
Model. And I like to know. So I have I have billions of queries.
Right.
And in some sense, you're saying so. Come up with a labeling, a way to classify the queries, then you'll answer the question, and you can test different classification methods out to sort of iterate over to find ones that you said, wow, you got the bad error rate on these. That's still interesting.
Yeah. So you can do that. I haven't actually done, and this is something I've been meaning to do for a while. It's kind of analogous to what you said, sort of a real active learning experiment here. And so I don't want to say, oh yeah, you're definitely good to go there. I would love it if it turned out that way. But I think that's more an empirical question at this point.
Some other mechanism that you thought of, that's exactly result.
No. So that setup is exactly what I would want to do as an experiment. Yeah, exactly what you said.
Any more questions?
Okay, good.